Let's look at the dimension theorem. For an m by n matrix A, the rank plus the nullity equals n. Here's why. The rank plus the nullity, well, the rank is the number of leading variables, and the nullity is the number of free variables. Well, variables are either leading or free. So when you add together the number of leading variables, which is the rank, and the number of free variables, which is the nullity, you get the number of variables, which is the number of columns, which in this case is n. Find the rank and nullity of this matrix A. Okay, the rank of A is again the dimension of the row space of A. The reduced row echelon form of A gives you a basis for row A because elementary row operations don't change the row space. So just count the number of non-zero rows in the reduced row echelon form. Okay, the reduced row echelon form of A looks like this, which has 3 non-zero rows. Thus, the rank of A is 3. Okay, we have 3 non-zero rows. The null space of A, which we denote by null A, is the set of all solutions x of AX equals 0. The dimension of null A is called the nullity of A. Now let's find the nullity of A. Method 1. Nullity of A is the null space of A, the set of all solutions of x of AX equals 0. So let's write that as a matrix equation. This leads to the augmented matrix, which looks like this. The reduced row echelon form is like this, which leads to this system of equations. Okay, so notice you've got x1 plus 3x3 minus 6x5 equals 0, right? This one. You shift the x3 and the x5 to the other side, and this is what you end up with. And if you do the same with these other two equations, you end up with this. x2 minus 20x5 equals 0, x4 plus 8x5 equals 0. Shift the x5 to the other side, this is what we end up with. Notice we can rewrite this system of equations in this way. So you can write it like this. If you throw in x3 equals x3 and x5 equals x5, factor out the x3 and x5, and we end up with this. Every solution to ax equals 0, that is a linear combination of -3, 0, 1, 0, 0, and 6, 20, 0, -8, 1. So these vectors form a basis for null A. The nullity is the dimension of null A. Since there are 2 vectors in the basis, 1, 2, the nullity is 2. Okay, here's method 2. This is another way to determine the nullity of 2, or the nullity. The dimension theorem tells us that for an m by n matrix A, the rank plus the nullity is n. A is a 4 by 5 matrix, so in this case n is 5. The rank plus the nullity is 5. Well, we calculated earlier that the rank was 3, so the nullity is 2. That's, of course, a much easier way to calculate the nullity. Suppose an m by n matrix A has rank k, then, here's some implications, the nullity must be n minus k, because the 2 of these have to add up to n. Any row echelon form of A has k non-zero rows, since the rank is k, and m minus k rows that are all zeros. They consist entirely of zeros. AX equals 0 has k leading variables, the rank is k. Sometimes we call leading variables pivot variables, so it has k leading variables, k pivot variables, and n minus k free variables. We can add statements to our long list of statements which are logically equivalent. It's this monster theorem of many statements. Let A be an m by n matrix. These statements are logically equivalent. A is invertible. The determinant of A does not equal 0. We saw a bunch of others. But we can add to this. The column vectors of A form a basis for Rn. The row vectors of A form a basis for Rn. The column vectors of A span Rn. The row vectors of A span Rn. The rank of A is n. The nullity of A is 0.